Okay, good evening. Thank you for the nice introduction. I am Simone Pirrera from the System Identification and Control Group, and today we'll talk about a work which I am developing during my PhD activities together with my supervisors Vito Cerone, Sophie Fosson, and Diego Regruto, which is titled Constrained Optimization via Controlled Multipliers. So basically we will go through a quick introduction to the main framework, then we will introduce the main considerations and results, and finally we will see some application to the training of recurrent neural networks, and finally we will draw conclusions. So basically these works investigate the relationship between dynamical systems, which are modeled by differential equations, and optimization algorithms, which are algorithms we use to find the minimum of a function, eventually subject to constraints. And most of the works in the literature which address this relationship concern with the analysis of the optimization algorithms using dynamical systems as a tool in order to study the properties of the latter. In particular, the most exemplar example is that of the negative gradient flow dynamics, which corresponds to the very well-known gradient descent algorithm. And studying these dynamics, mathematicians were able to prove that this algorithm converge towards a local minimum of the original optimization problem. We also have in the literature accelerated versions of these dynamics which are studied, and for what concerns constrained optimization problems, which is what we consider in our work, we have primal dual gradient dynamics, alternating direction method of multipliers, and many others. So, what is the objective of our work? Instead of analyzing some given optimization algorithm using dynamical system, we would like to set ourselves on the same framework, but rather find some systematic method in order to design new optimization algorithms which solve a particular class of problem of our interest. And in particular, the kind of problems we consider are equality-constrained optimization problems, which have this form, which we assume to be differentiable, but in general non-convex and therefore NP-hard. And not only it turns out that this can be done, but the way to do so is using control system theory. So we start by this very old but paramount importance result, which is the Lagrange multiplier theorem. Basically, this theorem says that if you have a local minimum x star, then you also have a vector which is called vector of Lagrange multipliers, lambda, such that this equation is satisfied. And this equation is called first order optimality condition. Inspired by this result and previous works on primal dual gradient dynamics, we then define this dynamical system. Basically, the rationale between this definition is that you define the states of this system to be the optimization variables for your optimization problems. The outputs are taken to be the value of the constraints, and the state equation is set to minus the same equation which appears on the first order optimality condition. Notice moreover that the vector of Lagrange multiplier is now a signal which depends on time, and we interpret this as the control input for this dynamical system. Then it is a very easy consequence of this definition that if you are able to find an equilibrium point for this dynamical system, by definition of equilibrium point, the first order optimality conditions are satisfied. And moreover, if this equilibrium point is such that your output is regulated to 0, you also have that your equilibrium point is feasible, which means that all your constraints are fulfilled. And so, on the basis of this parallelism between regulation and stabilization control problem and optimality conditions for optimization, we are able to conclude that any optimization problem of this kind is therefore equivalent to a control problem. And in order to solve this problem, what we can do is designing a feedback control system by properly defining a controller which drives the Lagrange multiplier of the system we defined in order to achieve this regulation and stabilization control tasks. And the fact that this controller drives the Lagrange multiplier of the optimization problem is the reason why we refer to our approach as the controlled multiplier optimization, or CMO. So let us now see what kind of optimization algorithms do we obtain for different controller design methods. First method that we consider is the proportional integral, or PI, controller design. This is a very easy kind of control design technique, which by definition requires that your input is set to a linear combination of your output and the integral of your output. So this immediately allows us to get a dynamic controller which is defined by a differential equation, as you can see in this slide. This is obtained just by taking a derivative with respect to time. And of course, due to the fact that this control strategy is very simple, we cannot expect this controller to be a good controller for any kind of plant which arises from any kind of optimization problem. But we are able to conclude that if we restrict our attention to a specific class of optimization problems, then we achieve what we like. And in particular, if we restrict our attention to strongly convex objective functions and affine equality constraints, then there will always exist some smart choice of the PI controller parameters, such that the closed loop dynamics provided by this PI controller is a unique, globally and exponentially stable equilibrium, which indeed corresponds to the global minimum of the optimization problem. And therefore, our closed loop equation, once integrated properly, will provide us with the solution that we desire. A few remarks about this solution. The first is that if you take the proportional gain of the controller to be equal to 0, you basically obtain the integrator controller dynamics, which is equivalent to the primal dual gradient dynamics, which is a very well-known dynamics which is studied in this context. And moreover, it is possible to show, within the proof of the previous result, that the exponential rate of convergence that we achieve using PI control is always faster than the exponential rate of convergence that is achieved by primal dual gradient on the same class of problems. More than that, after discretization of these closed loop equations, the algorithm which is obtained is a very simple iterative strategy, which is also very computationally and memory efficient. And lastly, I would like to remark that although this convergence is proven for the strongly convex optimization problems, experimental results shows that this is a valuable heuristic also for certain non-convex problems. And in particular, we have some numerical examples that this solved the NP-hard Shidoku problem, which is a mixed integer polynomial and very, very complicated. Another possibility to design this red controller we had in the previous slide is a more sophisticated method, which is feedback linearization. In order to apply this controller design technique, we need two assumptions. The first is that you have less constraints than optimization variables. This is very standard in the context of optimization. While the second is that the Jacobian of the constraints is always full rank, and this basically means that you don't have redundancy in your constraints. And as a consequence of these two assumptions, we can prove this simple lemma, which says that, to tell it in few words, the non-interacting control problem admits a solution, and in turn, you can design a feedback linearization controller. So, if we do this, we follow feedback linearization theory, which provides us with this controller. I will not enter into the details of this equation. The only thing that I would like to remark is that we have some degree of flexibility in designing this controller, because the calligraphic K in this equation can be chosen as we like, as long as it is a dynamical system which stabilizes the integrator dynamics. And doing so, we have, by construction, the first property that we desired from our feedback control system. And in particular, we have that our constraints will asymptotically converge towards zero, and therefore we will have some feasible solutions. More than that, if the calligraphic K in the previous slide is linear, we can prove that this convergence is also exponential. For what concerns instead the other issue, which is about does this strategy converge towards an equilibrium for the optimization problem, we are able to prove this second theorem. This basically says that if you have a point which satisfies the second order sufficient conditions for optimality, which are given here, then this point is a locally asymptotically stable equilibrium for the closed loop system. And therefore, you will have some equilibrium to which converging. So, this concludes the first part of my talk, which was more theoretical. And now I would like to enter into an introduction about a more practical part, which is related to the training of recurrent neural networks. In particular, we consider the system identification problem, which is about learning the behavior of a nonlinear dynamical system out of sampled and noisy data. Basically, when no information on the structure of this dynamical system is available, the most common and also reasonable approach is that of using some neural network-based structure in order to identify the model. And in this table, I reported a summary of comparing the features of the most common neural network-based models which are used within this context. It turns out that the model on the last row, which is called the neural network output error, which is a model which was proposed 50 years ago, but it's almost unknown in the current literature, is completely forgotten. Enjoys a number of good properties which are not shared by the most popular alternatives. But still, this model has the problem that in order to train it, we need to resort to an algorithm which is called backpropagation through time, which basically consists in the minimization of this cost function through standard backpropagation. And this unfortunately leads to the vanishing gradient issue, and therefore to poor performances of the final model. In order to get rid of this problem, what we do propose is reformulating the optimization problem as an equality constrained optimization problem in an augmented set of optimization variables, and then apply our feedback linearization based CMO algorithm in order to perform the training. And if we do so, we are able to obtain a training algorithm which surprisingly maybe, performs much better than standard LSTM-based identification on our simple pendulum identification example. More than that, I would like to remark that the training effort, the computational effort required by the training is comparable to the LSTM one. We have 2 minutes of training for both methods. So to conclude, we propose a method to solve a quality constrained optimization problem, which is based on control theory, and we apply this to the training of recurrent neural networks. And when we will consider future work, we will extend this method to non-differentiable and inequality constrained problems. We will address the problem of handling noisy input data in neural network output error based identification methods, generating a new model which we will call neural network error invariables. And finally, we will apply that to the problem of directly designing a controller from data. This concludes my presentation. Thank you for your attention.